Okay, so we've talked about the findings that we had studying the moon. And next question that we wanted to ask and then answer is, where did the moon come from? Because our moon is nothing like what we would expect looking at the other terrestrial planets. Mercury and Venus have no moons at all. Mars doesn't really have any moons. Yeah, it's got 2 moons, but both of them are probably captured asteroids. So our moon is really the size of a moon of the gas giant planets. It's one of the larger moons in the entire solar system, and yet we are a fairly small planet, definitely compared to the gas giants. Remember, you could fit 1,000 Earths inside of Jupiter, nearly as many inside of Saturn, and Uranus and Neptune are both huge compared to Earth. And yet, how do those worlds rank moons the size of ours, and nothing else small has a moon like ours? So, the big question, where does our moon come from? So before Apollo went to the moon, there were 3 main ideas for where the moon came from. And one idea was co-formation. And that is that the stuff was swirling together to make planets, because this was the original idea as to how planets formed, is in the cloud of material surrounding the protosun, it was clumped up and made planets. Now we think, as we said, maybe Jupiter did that and maybe Saturn did that, but the other planets really we don't think formed that way. But at the time, when they went to the moon, this was one of the ideas they were thinking of how the Earth and other planets formed. And so they thought all the stuff swirling together to make Earth just clumped up and made 2 things. That would make the moon and Earth. The other idea is that the moon itself formed after the Earth formed, and then a chunk of the Earth broke away and made the moon. And that idea was actually championed by Charles Darwin. Remember, Darwin was the one who figured out that the moon is gradually spiraling away from Earth. He did this theoretically. And so he proposed, for example, that now he thought it was a lot faster than it really is, but he proposed that the moon broke away from the Earth, flung out into space, and that the big giant hole it left behind was the Pacific Ocean. At the time that he made that pronouncement, all they really knew about the Pacific was it was huge and very deep. Capture. The idea would be that the Earth formed, however it formed, and then the moon formed somewhere else in the solar system, and as it was passing by, it got caught in Earth's gravity into orbit. Okay, so let's investigate each of these ideas. Co-formation. So the moon formed out of the same material that was making Earth. Well, if that's what happened, then it should have the same basic angular momentum as the Earth, meaning that the moon would form directly over the Earth's equator, which obviously is not correct. The moon's orbit is really close to the ecliptic, not close to the equator of the Earth. So the moon's orbit is closer to lined up with the rest of the solar system than it is lined up with Earth. So that doesn't seem to fit. Secondly, if the moon formed simply the same stuff at the same time as Earth, it should have precisely the same composition. In other words, it should have the same minerals, it should have the same proportions of everything. And as we saw, that's not entirely correct either. The moon doesn't really have a whole lot of bizarre minerals that Earth doesn't have, other than some that degrade in our atmosphere, and so we expect that. But it's missing a few minerals that Earth has. It's missing several things that are volatile minerals. It also does not have the same proportion. Remember, the moon has got way different crust and mantle proportions. The moon's core is very, very tiny. It's a teeny tiny portion of the moon, way smaller than Earth's core. And most of the, in fact, even that core seems to be contaminated with mantle-type stuff, sulfur. And so, if this were what happened, then we would not see what we see on the moon. So that's probably not what happened. Fission. Okay, come on, people. I mean, you know, how often are you walking along, you trip and fall off the Earth? Okay, so, you know, you don't just fly off, you know, a chunk of the Earth doesn't just fly off into space. That's not going to happen. You know, even if the Earth were spinning so fast that centrifugal force would throw a big chunk of it out, then that's still not going to account for the moon, because the moon, if this is exactly what happened, if the chunk of the upper part of the Earth flew off, that would give you a moon that's mostly crust and mantle stuff. Yeah, that would fit, okay, but it would also throw it into an orbit right over the Earth's equator. That's not what we find. So that too doesn't fit. Okay, the other thing is the moon would have precisely the same mineral composition as Earth rocks. Again, this is not what we find. This is not the moon that we see. And so that's, again, we see that this doesn't seem to fit. Okay, so that idea also doesn't work. Okay, capture. The moon formed somewhere else, passed by Earth, and was captured in Earth's orbit. So that idea was what was left. Okay, now the problem is, if that is exactly what happened, then the moon's isotope ratio would have been way different than Earth's isotope ratio. That's not what we find. The moon rocks that were brought back to Earth had the same basic isotope ratio as Earth, indicating the moon formed where it formed. Okay. Secondly, we would also expect some mineralogical differences. We don't have, we would not expect the kinds of mineralogical differences that we found. We would, in other words, if it formed somewhere else, there's nothing that would say that there'd be no volatiles on the moon. So that doesn't seem. In fact, a lot of the other things that are out there, particularly formed farther out from the solar system, have lots of volatiles. And so that too does not fit with our observations. So these were the three ideas they had before the Apollo missions. All three were ruled out by findings from the Apollo program. Well, a few years after the last Apollo mission, then two different groups of astronomers, Hartman and Davis in the U.S., and then Cameron and Ward in the U.K., both independently came up with the same basic idea. And that is, okay, when the Earth was very young in the early solar system, there were a lot of big planetesimals flying around. What if a really big planetesimal were to hit Earth? Something the size of Mars. Then what would happen is it would slam into Earth. Now, the thing is, the Earth is still going to be vastly bigger. You could fit 8 Marses inside of Earth. So even something Mars-sized hitting Earth would not destroy Earth. It would massively damage Earth, but it would not destroy Earth. What would happen is, going through computer simulations, was it would slam into Earth, particularly if it's a glancing blow, then it would scoop away giant blobs of Earth into space, and these blobs would be tossed into orbit outside of Earth, and so you would scoop away large chunks of the mantle and crust of the Earth. And so that those large chunks would be blown up. A little bit of the heavier stuff, like the core material, would fall back. Okay, and what would happen is you would have an Earth that has a thinner crust, because you're going to melt the whole planet when you do this. And so so the lighter stuff's going to float to the top. In fact, you might have it clumpy so that a lot of the crust stuff ends up on one side versus the other clumpy, like continents. Okay, Earth is the only planet in the solar system with continents. Everything else is a more uniform crust. this would leave Earth with an unusually thin crust. In fact, Earth does seem to have the thinnest crust of any planet in the solar system. It would also make the stuff out in orbit out there mostly crust and mantle stuff. Okay, gravity would pull all this stuff together eventually and would make one object, okay, out there. And the gravity of the sun and the other planets would cause all this stuff around Earth to line up close to the ecliptic instead of over the equator of the Earth. And those are all things that we see. And so this idea, what we call the collision ejection model, has now come to be the dominant explanation for where the moon comes from. Now, the thing is that this was proposed in the 1970s. We've not landed on the moon since then. We've only, in just the last few years, started sending more spacecraft to the moon to study it in greater detail. Now, the other thing about this model that was very, very good was it also would make a very high heat event in this whole thing, which would vaporize any of the volatile minerals on the moon. That would leave the moon with very few volatiles. It would also leave very little water because that was also largely vaporized. Okay, and so compared with Earth. And so, again, these findings seemed to be consistent with, in other words, findings from the Apollo rocks and regolith studies. The samples we brought back seem to be very consistent with this model for the formation of the moon. And this is one of the things we want to do with our missions that are now going to the moon, that are now landing on the moon. The Chinese landing on the moon. U.S. wants to land on the moon again, too. Private companies looking at landing on the moon. With the landings on the moon, even if they're not manned landings, unmanned landings, and then eventually we want to send a manned mission back to the moon and actually study the moon in far greater detail. Technology has really come a long way since the 1970s, and so we want to be able to study it in greater detail. Now, I will admit, some of the moon rocks that were brought back have been very poorly studied. Some of them they've been basically holding aside for later technologies to come along to study, and so some of these rocks are being studied in ways today that were not possible back in the 1970s. And so, 50 years ago, we couldn't do some of the things that we're doing today, mineralogically studying these rocks. We are studying some of them now in greater detail, but again, these were rocks that were picked up along the surface of the moon in 6 spots. Now, granted, some of these rocks were along the rays of a crater, so there were stuff that were tossed into that area from far away, but again, they tried their best to pick up a variety of rocks of different kinds to give us as broad of a sample as possible. But the reality is, if you're just going to grab rocks from 6 spots on a world, no matter how well you pick those 6 spots, you're not going to learn everything there is to learn about it. So that's one reason we need to go back to the moon and study it in greater detail. But this is what we have found. And so this is the idea that we have for the origin of the moon now. Collision ejection. About 100 million years after the planet's formed, so early in the solar system, an object nearly Mars-sized, and everybody wants to name the thing, so somebody named it Theia at some point, though that's really not an official name. So this collision with Earth is part of what stripped Earth of things like iridium, platinum, gold, and so forth that would have been in the Earth's crust and mantle. So practically all of those kinds of things, iridium, platinum, and gold, silver, whatever we have like that on Earth, actually comes from meteorite impacts. So this impact, and this is why a lot of these things are actually visible, actually apparent on the moon's surface itself. So this is very consistent with what we really see with the moon. So this is our leading model right now.